Welcome to Lecture 4. In our class, the next two lectures will be dedicated to the so-called Hille-Yosida-Ray theorem. This theorem is in a way the opposite of what we did so far. Up to now we were starting from a Markov process basically, and we were identifying a structure which is a semigroup of operators which describes the statistical properties of such a Markov process. And we were starting with the analytical description of properties of such a semigroup. Then the next step was to start from a semigroup and ask whether that gives rise to a Markov process. And we also introduced already what is called the generator of a semigroup. And we identified the generator of certain Markov processes in particular cases. And today, as basically the completion of our abstract theory about the relation between Markov processes and semigroups, we will investigate a little further the decisive role that is played by the generator, which we introduced already. And the Hille-Yosida-Ray theorem tells us, or gives us a sharp characterization when a certain operator with an appropriate domain on the space of continuous bounded functions, vanishing at infinity, when this operator is actually the generator of a semigroup, it will tell us that this semigroup then is unique, which in total allows us to basically identify a semigroup of operators, so a Feller semigroup as we learned, with the corresponding generator. And as a consequence, it will allow us to identify basically a Markov process with the corresponding generator, which then ultimately leads to the conclusion that, at least in theory, everything we would want to know about a Markov process, and therefore a Markov process which appears in physics or in nature, that everything we would want to know about the Markov process is essentially encoded in the generator. So therefore, the theory of Markov processes is a theory of the corresponding analytic theory of generators. And that will be finally completely justified by means of this Hille-Yosida-Ray theorem, which will be the subject of this lecture and the subsequent lecture. The lecture today will be dedicated to the statement of the Hille-Yosida-Ray theorem, and it will be dedicated to discussing two examples, how we can apply this in order to convince ourselves that certain Markov processes can be constructed. And the subsequent lecture, which will be lecture 5, will be devoted to the proof of the Hille-Yosida-Ray theorem. Throughout this lecture and the next lecture, and basically more or less almost the entire rest of this semester, we will from now on assume most of the time that the state space that we are working on is in fact a locally compact and Polish space. So I discussed what a Polish space is. By locally compact we mean, if we have a metric space for instance, that the closure of balls are compact subsets of this set. And as we shall learn below, one important property of the generator of a Markov process is that it satisfies the so-called weak maximum principle. That's, if in a way, the only theoretical result of today, which says that if we have, in fact, a generator of a Feller contraction semigroup on such a topological space, which is locally compact and Polish, or to be precise, the actual contraction semigroup, of course, operates on the collection of continuous functions which vanish at infinity on this locally compact Polish space, then such a generator necessarily satisfies what we shall call the weak maximum principle. And it states is the following property, namely, if we have a function u in the domain of the generator, and if we pick a point in the state space where the function u assumes its maximum, such a point will always exist by the boundedness and the continuity of the function u, then the application of the operator to that function evaluated in this position is necessarily non-positive. So let's say it again. So if we have a generator of a Feller contraction semigroup on such a space, then this generator necessarily satisfies this maximum principle, which is stated as follows. So if we do have a function which assumes its maximum in a particular point, then the A operator applied to that function, evaluated in that point, must be non-positive. And a side remark, sometimes also people invoke only what is called the positive maximum principle. This is the corresponding property that is encoded here, but only required to hold for such functions which are non-negative anyway. But it turns out that for our purposes, it is sufficient to work with this version of the maximum principle. Okay, the proposition says that if we have a generator of a Felle contraction semigroup on such a space, then that generator will necessarily satisfy this weak maximum principle. Let us prove that. It's a simple proof. Okay, let us pick such a function u from the domain of the generator. And let us pick such a position x0 where u assumes its maximum. Then, if we pass to the function which is obtained by shifting the function u by this maximum value and subtract the function u, then this is a new function u bar. It's shifted and reflected, a shifted and reflected version of the function u. By definition, it's a non-negative function, and therefore, if we apply our semigroup, our Felle semigroup, to such a function and evaluate it at any point, that returns a non-negative value. Assume that part, or recall that part of our definition of a Felle semigroup was that it preserves positivity. Now, if we write out again what this u bar really is, it's a sum of two functions. One is the constant functions multiplied by a constant. That's the first summand, and the second summand is just the u function again. So we just use the fact that the p operation is a linear operation, where here in the first summand we have the p operation acting on the constant function 1, and in the second summand we have the p operation operating on the function u. And if we rearrange just this inequality, then we find that pt of u evaluated at x0 is no bigger than this constant, which is inside the semigroup, which we can pull out by linearity, times pt of 1. And recall that our definition of the pt was, or we want to assume that p is a contraction, which in particular implies that the one function is mapped onto a function which is no bigger than 1 anywhere. So therefore this thing on the left-hand side, on the right-hand side, is no bigger than u of x0. So in particular, we have that ptu at x0 is bounded from above by u at x0. And now if you recall the definition of the generator, it's just taking the derivative of this pt function at t equals 0. So just if you do the difference quotient, which features these two terms, take the difference of the two and divide by t, let t tend to 0, you end up with a non-negative correction, with a non-positive value, which gives the assertion right away. So we see that any generator of the contraction Felle semigroup will satisfy this weak maximum principle as we had stated it. After this preparation, we can state the Hille-Yosida-Ray theorem, as we had announced, and it gives a characterization of a linear operator to be the generator of a contraction Felle semigroup. Okay, here goes the statement. So let A, an operator together with a defined domain d of A, be a densely defined linear operator on this space of continuous functions vanishing at infinity. Then the following two statements are equivalent. First is that this operator is in fact the generator of a Felle contraction semigroup, which is the same as saying that this operator satisfies the following three properties. First of all, the domain of A is a dense subset of A, which is essentially redundant because we had it already here in this in the assumption of the theorem, so therefore the theorem is not entirely properly phrased. But okay, so the first condition is that the operator A has a dense defined domain. Second, for all strictly positive lambda, the range of this operator lambda minus a. So lambda, whenever I write a lambda, this is to be understood as a lambda times the identity operator. So lambda times identity operator minus a as an operator from this subset of the continuous functions. So suppose here is your graphical representation of the set of continuous functions which vanish at infinity. And then somewhere inside you have typically a strict subset, which is the domain of the operator. And we can now define a map for any positive lambda, which takes a function f from the domain and maps it into lambda f minus af. And what we want is that this lambda minus a operation as a map from the domain into the space of continuous functions, that this fills up the space of all continuous functions which vanish at infinity. So this is the full range condition. So condition 2 is sometimes called the full range condition. It says that this lambda minus a operator has full range. And the third condition that we want to, or that we need for this operator to be, in fact, a generator of a Feller contraction semigroup, is that it satisfies this weak maximum principle as we had stated it. If that's the case, if either of the two assertions is correct, which are equivalent, then this operator is closed. We had already seen that in the previous lecture, or the previous lecture before, and the corresponding semigroup to which this operator is, if you like, this semigroup is unique, which in other words is to say that whenever you find a semigroup which has this generator, then this semigroup must be uniquely determined. So therefore the generator gives rise to a unique semigroup. So the Hille-Yosida-Ray theorem gives a full characterization of all those operators on the set of continuous functions which vanish at infinity, which actually do generate a Markov process, which do generate a Feller contraction semigroup, which, as we know, is in one-to-one correspondence with a Feller Markov process. This is the property of, this is the statement of the Hille-Yosida-Ray theorem. And so, therefore, if you want to construct a Markov process, one way to do it is to propose a certain operator on the state space, or on the space of continuous function vanishing at infinity on the state space, and check whether these three conditions are satisfied. And that's what we shall do in two examples in today's session in order to familiarize ourselves with this method of constructing Markov processes. Okay, we start with a variant of Brownian motion, which is then called the reflected Brownian motion. And we will construct such a process by identifying the corresponding generator. And in the exercises, we will show how this operator, or how the corresponding induced Markov process, is related to the classical Brownian motion. So it will be a cousin of Brownian motion, which we have not encountered so far. And we will introduce this cousin of Brownian motion by proposing a certain generator on the set of continuous functions which vanish at infinity on an appropriate state space, and by checking that this proposed generator satisfies the assumptions 1 to 3 that appeared in this characterization of generators in the Hille-Yosida-Ray theorem. Okay, the reflected Brownian motion, just to draw you a picture, if I draw a realization of the reflected Brownian motion, it will look like this. So I draw the t for the time axis, and I draw the real line. In this case, I need only the non-negative real line as the state space. And so the trajectories of the to be constructed reflecting Brownian motion will look like this. So whenever the process hits the zero level, then it is reflected, and it is doing a trajectory north of the t-axis, or r equals naught axis. So in other words, we could think of a Brownian motion which does a motion like this before it comes back to zero and does a positive path. And so in other words, what we want to do, the reflected Brownian motion would follow the positive path of Brownian motion as long as the Brownian motion happens to be on the non-negative real lines. And then whenever it has an excursion towards the bottom part, the lower part of the half space, then we replace this Brownian motion by the corresponding positive trajectory, just by the reflected Brownian motion. So this is what we call the reflected Brownian motion in one dimension. And we want to investigate this process a little later as really a process with, as a Markov process. But before we do that, or we want to investigate this, or we start the introduction of this process by proposing a generator, of which we hope that it actually corresponds to these red trajectories that we observe if we do this reflection procedure. So the actual state space for this process, the collection of points or states where this process can assume, in this case will be in the non-negative real line. This process will be constructed so that it will never be below zero. And hence we discuss now the case of continuous functions on the non-negative real line which vanish at infinity. In this case, vanishing at infinity really means that they vanish at plus infinity, because vanishing at zero, that's not an infinite point, so it's just a collection of points, a collection of functions which are continuous and which decay to zero when you go sufficiently far outside zero. And as the domain of the generator, which I want to introduce, I suggest the following collection of functions. I want to consider the function of those continuous, the subcollection of those functions which are continuous and vanish at infinity, not only by themselves, but also that's also the first and second derivatives are continuous. They exist and are continuous and vanish at infinity. Where second derivatives and third derivatives on the left boundary point at zero are to be understood as one-sided derivatives. So I want a function, so let me say it again. My domain shall be the collection of those continuous functions on the non-negative real line who are differentiable up to second order everywhere, where differentiability at zero is to be understood as one-sided differentiability. And I want that these differentials, or these functions, these differential functions, are also functions which vanish at infinity. And I want to assume an additional important condition that the first derivative at zero, so the right derivative, the first right derivative of these functions is zero. So in other words, I want to consider functions as observables which are continuous and differentiable twice even, and I want that they have zero slope when they start from the origin. So such a function, if you would zoom in, you would probably understand, or that's what I meant. It's a slope zero function. So it starts with a zero slope at the origin, and then it can do whatever it wants, provided it remains twice continuously differentiable and it is sufficiently vanishing. And so this function here, for instance, which clearly has a non-zero slope when it starts at the origin, that function would be in the domain of this operator, and this function would not, because this function here does not have a zero slope at the origin. Okay, so my domain of this generator, which I want to construct for this process, for this Markov process, is the process of all functions with the regularity that I imposed, which additionally have to satisfy that they have zero slope at the origin. And as when the generator, the actual assignment of a generator to such functions is, as in the Brownian case, the half of the second derivative. And then I claim that this domain, together with the assignment A, is in fact a Felle generator on the space on continuous functions on a non-negative real line. And later we will see that this is actually really the generator of this reflecting Brownian motion. Now, pointing towards future understanding, so there is a version of this process which has continuous paths. It's called the reflected Brownian motion, and it can be realized simply as the absolute value of a standard Brownian motion. Up to this point, we did not have a conceptual description as a stochastic process of the absolute value of Brownian motion. We can construct it, but we haven't fully understood it, or we haven't even introduced it, and we cannot describe it by conventional stochastic differential equations theory, for instance, but we can understand this process well as a proper mathematical object through this semigroup theory that we are about to develop. And let me say it again, I claim that this is the corresponding generator as a Markov process. Okay. The precise relation, as I said, towards this picture with the red trajectories, if you like, that will be established a little later. But at this point, I just have the claim, that's all I said at the moment, as a proper claim, is that this is a Feller generator. So in order to convince myself it is, in fact, a Feller generator, I can use the conditions, the statement of the Hille-Yosida-Ray theorem, which gives the three criteria which need to be satisfied. The first criterion is the question about the closed, the dense domain. So what I have to show is that any function which is continuous and which vanishes at infinity on this non-negative half line can be approximated by a function which is in the domain of the generator. Right? So I recall what I want to show is that that's my first condition, that the domain of definition is dense, in this case in C naught R non-negative, which means I need to find for all functions f in C naught of R, I need to find, if like, a sequence or a family of functions fk which belong to the domain of the generator, such that fk and f are arbitrarily close in the infinity norm, in the supremum norm, for any positive epsilon. If that's the case, then I have an approximation by the sequence of functions in the domain which approximate the given function in the norm in the supremum topology. Okay, so therefore let's take an arbitrary function which vanishes at infinity, which is just continuous, and let's try to find an approximation by functions which are in the domain. And the key idea here is to study the symmetric continuation of this function. So this is my function that I start with here. And what I want to pass to now is the symmetric continuation of that function by just reflection towards the entire non-negative, towards the entire real line. So this is just a function which I obtained from the initial function f, but just reflecting its graph towards the left part of the Euclidean plane. And this extension by symmetric or by reflection is denoted with this upper bar, f bar. So for every function f in the domain, or for every function which is continuous on the non-negative real line, I can consider the corresponding symmetrized extension. And on the non-negative real line, on the full real line, I have a wonderful process which I can use now, and which has all kinds of information that we have already studied, the Brownian motion. So I shall now use the Gaussian semigroup for the full Brownian motion, which is as we know, a Feller process or a Feller semigroup on the full Euclidean line. And I can apply this operator now to this function, which was obtained by symmetric extension. This function, which is written here, is now a function which lives on the entire non-negative real line, and I can restrict this function. I can just evaluate these continuous functions only to arguments which again lie in the non-negative real line, which altogether gives me a function f epsilon, which is defined only on the non-negative real line, but it is a continuous function. And then I can convince myself easily by the properties of the full Brownian motion and its semigroup, which is just the Gaussian semigroup, that this function f epsilon is twice continuous differentiable on the full space, and so in particular if you like, on this half space. And then also, this collection of epsilon approximations converges to F just by the continuity of the Feller semigroup for the full Brownian motion. So this convergence is correct, which is just a consequence of the even better convergence we have on the full space for the non-restricted objects. And then also by symmetry, since this function is reflection symmetric, also the F epsilon function will be symmetric with respect to reflections, but it's a differentiable function, so therefore a function which is differentiable at the origin and which is symmetric with respect to reflection must necessarily have vanishing slope at the origin. So therefore, the F epsilon function is a function which is in the domain of the operator, and it is sufficiently, or it's arbitrarily small in distance towards the F function if epsilon is chosen, or the approximation parameter is chosen small enough. Which altogether gives us this conclusion that in fact the domain of definition of this operator is dense. So if we want to have a picture, what's really going on is something like this. So I have an arbitrary function which may be any wild and probably not even smooth, but continuous. Then I do a symmetric modification by a function that will be in a way my approximation. I do a symmetric modification of this function, which will possibly look like this through this heat kernel, as we say, approximation in this symmetric fashion, which is made in such a way that in uniform topology, so in the sense of uniform convergence, this sequence of F epsilon functions converges to the F function, which, let me say it again, proves that the domain of definition of this operator, A, as we had said it, is in fact dense. The next task is to show that this operator satisfies the full range condition. We want to show that lambda minus this generator has full image in this set of continuous functions. So for that purpose, choose any lambda positive. And given our function f as before, we consider the symmetric extension of the function to the full line. We operate with it. We act with the full Gaussian semigroup on it, and we compute with it the analog of the Laplace transform. So we take the time integral of this operation of the full Gaussian semigroup on this symmetric extension, integrated over the whole time interval from 0 to infinity, but weighted with this exponential decaying factor. And then this function, which is a function on the full Euclidean line, will then be restricted to the non-negative real line to give us a function which we shall call G lambda, which is the function we want to study on the non-negative real line. And what we know is that since the G bar function, so that's the function which we obtain by the symmetric extension using the conventional semigroup, since we have already discussed this case, how the conventional semigroup for Brownian motion operates, we know that the G bar lambda function is a function which is twice differentiable and vanishing at infinity together with the first and second derivative, and so therefore the corresponding restriction, which is just the G lambda function, has the same properties on the restricted interval. And we also know, again by the previous argument as before, that the G bar function will be a symmetric function with respect to reflection at the origin, so therefore, since it is smooth, it must have zero slope at the origin, which in particular implies that this G lambda function, the restriction of this G bar lambda function, is in the domain of the generator. Now we can therefore evaluate the action of the generator on this G bar function. Well, we know that by our prescription, the generator, our particular generator on such a G lambda function is given by 1/2 times the second derivative, which happens to be the same definition of the Brownian motion generator, but in Brownian motion case on the entire line. So if we consider the corresponding function on the entire line and we write down the relation that we know for this resolvent, which we had effectively considered for the full Brownian semigroup, we know that G bar lambda is a solution, or is the resolvent for the f bar function. So it solves the corresponding equation, which is this resolvent equation for the full Brownian motion. This is exactly what we write here. This is just the full resolvent equation for the full Brownian motion. But this is, of course, an equation which we can also restrict for arguments which belong to the non-negative real line. So therefore, if we restrict to the non-negative real line, we find this equality, where we have omitted to write the G bars or the bar notation, because it's by our definition it's just the f alone if we restrict here, and if we restrict the f bar to the non-negative real line by choice of f bar, this is just the f, and by definition of the G bar, the G bar restricted to the G, or by definition of the G, in fact, the restriction of the G bar to the non-negative real line gives us the G in here as well, which happens to be the prescription of the generator of this function G lambda. Yes, the prescription of this generator evaluated on this function G lambda. So we see that, in fact, for any function f we have found, and for any lambda, we have explicitly constructed a G lambda, which belongs to the domain of the generator of this reflected Brownian motion, which is so that if we apply lambda identity minus a, where a is the generator, to G lambda, we retrieve the f, which is nothing but to say that for any function f we find such an image, or in other words, this operator lambda minus a satisfies the full range condition. Finally, we have to show that this generator satisfies this weak maximum principle. Okay, namely, we have to show that if we have a function which is in the domain of this operator, and if it is so that we have an x0, so a position in state space where this function u assumes its maximum, then we want to show that then necessarily the operator applied to that function evaluated at that point gives a non-negative value. Okay, so if we have such a point, we have two possible cases. Either the point is in the interior of the half-line. Okay, in this case, since u is first and second order differentiable by the classical first order calculus class, calculus class, we know that the first derivative in such an extreme point of the function must be 0, and the second order derivative in a maximal point must be non-positive. This is a necessary condition for a supremum, or a maximum, that the second order derivative of u at this point must be non-positive. But this second order derivative, happens to be exactly the prescription of our generator, so therefore in this case the weak maximum principle is satisfied. This was the case when x0 belongs to the interior. Now, if x0, this maximal point, or the argmax of u, happens to be exactly at the left boundary, which is the only case that's left to be considered, then by the fact that u belongs to the generator of the domain, we can assume it's just granted that the slope of this function vanishes at the boundary point, at 0. And also in this case, the value of the generator, or the assignment of the generator, is just a second order derivative, and we have to convince ourselves that this is non-negative too. Okay, but that is then, if you like, the simple consequence of the approximation of the second order derivative by difference quotient. Here in second order, recall that here I just use the Taylor's formula, if you like, that tells me that this one-sided derivative, second order, can be approximated by this difference quotient. Well, let me say it again, the first order derivative vanishes in this formula because the function u is supposed to lie in the domain and therefore has zero slope. So therefore my Taylor formula in this particular case simplifies to look like that. Note that we have a second power of h here. But since x naught equals naught is a local maximum, this difference quotient for any positive h is a non-negative number, and therefore the limit is a non-negative number. The limit exists because we know that u is second order differentiable, at least in one-sided sense. So hence I have convinced myself that also in this case the function, the second derivative or the generator applied to that function in the point of possible maximum is non-negative, which means that the generator here in this particular case satisfies the weak maximum principle, and altogether we arrived at the conclusion that this is in fact the generator of a Feller semigroup. The next example is much simpler, and it connects to our theory of Markov chains on discrete state spaces. Here we want to consider effectively Markov processes, time homogeneous Markov processes, which are defined in continuous time parameter, but which have a discrete, or in this particular example, even a finite state space. Okay, let's consider a time continuous Markov chain on a finite state space as follows. We consider just as a state space a finite collection of states, just as we did in the situation of Markov chains. So we consider now, if you like, the setup of a Markov chain in finitely many states. And we enumerate these states as numbers from 1 to n. And suppose we want to consider a symmetric situation, which is a slight simplification of the general case, but okay. So we want to consider the case when we are given an array of non-negative weights for each pairs of points I and j in the state space. So we're given a collection of Cij values. Cij are to be interpreted as conductances, if you recall our connection between Markov chains and electrical networks. So suppose for every possible, so we have, if you like, we have a network of different nodes, and these nodes carry names I or j, and we have finitely many of such nodes, if you like. And between every node I and j, we have a wire, and the conductance of this wire is denoted by Cij. That's a non-negative number, and it's as a function in these variables, it's assumed to be a symmetric function. And then we want to introduce an operator, in fact a linear algebra operator or just a matrix. So if we have a function f on our state space, here the state space is finite, and any function on a finite collection of points can be represented as a vector. And now I want to introduce this linear operator on such functions, on such vectors, so namely as follows. So if I have a function f in the states, which is just a vector indexed by these states I to a, then af, the operation that I will introduce now, operation A applied to f evaluated I is defined to be the sum of these differences fj minus fi, where sum over all states j from this state space. I keep the I fixed, I do this fj, the difference of fj and fi, and I multiply this with the weight Cij. That's now my proposal of an operator. I can rewrite this operator also in the form that it's the same sum fj minus f of I times Cij over Ci, where Ci is a common factor which I pull in front of this matrix. And here I made a mistake. I should write it as a Ci in front, of course, Okay, the Ci here is in the enumerator, where Ci is the sum of these appearing weights Cij when I keep the I fixed and sum over the j. So that's just a certain linear algebra operator, so it can be represented as a matrix if you like, and I want to make the claim now that this A is in fact the generator of a Feller process on this state space E consisting of only finitely many states. And of course, this is just a very shorthand notation for saying that A is a Feller generator on the collection of continuous functions on this finite state space, which vanish at infinity. But as I just said, the set of collections of functions on a finite state space is just to be identified with the corresponding vector space of vectors of the dimension of the cardinality of this space. So I'm claiming that this simple operator here is in fact the generator of a Feller process on this finite state space, which is induced from this weights Cij. Before I show that this is in fact a Feller generator and fits perfectly into our theory, I would like to complete the connection to our theory of Markov chains, namely in the particular case when this Ci is just a common lambda and depends not on I, we can also write the whole thing AF as a lambda, which is this common prefactor lambda times PF minus F evaluated at I, where Pij is now this normalized transition matrix Cij, which is a stochastic matrix, and we see that this is this operator AF is exactly this operator which appeared, for instance, in exercise 9 of our first class on stochastic process from previous semester, when we were dealing with what is called Poisson subordination of Markov chains. So this is, and we will discuss this in the exercises, this is the generator that corresponds to making a time-discrete Markov chain a time-continuous homogeneous Markov process by a Poisson subordination with a Poisson process of parameter lambda. So, the take-home message of this is that, yes, our theory of Markov chains on discrete spaces blends in naturally into this theory, and we even retrieve our old theory modulo this passage to time-continuous parameterization, and retrieve our old theory, and connect to the old formalism. Okay, let us now show that in fact this operator, which we had introduced here, is in fact a Feller generator. And again, we will do that by checking that these three conditions of the Hille-Yosida theorem, which characterize generators, are satisfied. So let's recall on what function space we are actually working. We are working on this space of continuous functions, which are in finitely many states, which we equip with the infinity norm, which is nothing but, since we work on on discrete or finite state space, we work with a discrete topology, so therefore all notions of convergence are trivial, or the conventional notion of convergence for points. We are dealing with the collection, or our function space is identified with the space of all vectors of dimension n, where the ith coordinate of a vector is to be understood as the value of the corresponding function on the ith point in function space. And we work there again here also with the supremum norm on these finite vectors. So the supremum, the maximal difference in absolute value between two functions on this finite state space corresponds to the maximal absolute value distance of two coordinates of the corresponding vector representations of these functions. And our operator A is written here once again. That's our representation of the operator. And it is to be understood, of course, that this operator is defined for all functions, for all vectors f. So therefore, it is automatically densely defined. In fact, the domain of this operator is the full vector space Here we have the case where the picture that I was drawing before about a certain function space where we have a certain strict subset which defines the domain of the operator. In this case, this is equal to the domain of my operator A. Every function f can be inserted into this formula. That's my proposal, at least, for this operator. And I can write this formula for any function or for any vector f because it's just a finite sum, which is, of course, well defined. So therefore, the first condition of the characterization by Hille-Yosida-Ray theorem is automatically satisfied. We want to pass to the second condition, which is again the full range condition. So we want to show that for any lambda positive, the range of this operator is the full Euclidean vector space of dimension n. That's what we have to show. And we shall do that by using the simple linear algebra or the linear algebra relation that a endomorphism from a vector space into itself has full range if it is injective. And we will show now that this operator L in fact is injective, which then proves this theorem, this assertion. Okay, let's show that this operator is in fact injective. For that purpose, assume we have found a function f, which is mapped by this lambda minus a to the zero vector. Well, then of course we can take the inner product of this zero vector with the vector f again, which then returns a zero. But we can write this zero, this inner product, also in slightly different form. First, we decompose this lambda minus a operation into a sum of two operations, namely lambda identity for the first inner product, and then we have a second inner product which involves these a operator applied to f, inner product with f. If you write that, we get the double sum for the second part. The first part, of course, is just lambda times f squared, because we have the f taken into the product with f itself, gives us a lambda f squared for the first part, and the second part is a minus, which comes from the minus in between here, and then we write the operator. That's the operator a applied to the function f evaluated at position I, where the j summation is coming from the definition of the operator, and then we have the summation with respect to the I index as a consequence of the inner product that we take here with this f vector. So that's writing out this second component of this inner product. And we have a closer look at this second component. The punchline will be that this second component allows a symmetric description. So in the following lines, I will argue that this Cij sum and so forth can be equally written as a minus 1/2 times the symmetric sum over all I and j with the Cij weights in front, and then this is hit with fj minus fi in squared, in brackets squared. If that is correct, then I can write, including, that's important, the minus sign here in front. So then I can replace this sum, which appears here, this whole sum, I can replace this by this expression which is symmetric with respect to the I and j indices, and in particular it comes with a negative sign, so that in altogether I'm ending up for this inner product with this representation. And if I look at this representation or at this formula, I find that this immediately implies that f in fact must be 0 for lambda positive. Why? Well, if, as we had started with, this whole thing is 0, then this 0 is written as the sum of two non-negative numbers. The first number is obviously non-negative because it's a positive factor times the norm squared. And the second number is also non-negative because here we have some squared numbers which are multiplied by non-negative weights Cij, and then we take the sum of that, which altogether gives a non-negative number. So here it's important that the Cij are non-negative, else the argument doesn't work. So therefore, we conclude that if that inner product is 0, then all constituents here, all the components on the right-hand side need to be 0, which in particular implies that the f norm, that the norm of the f must be 0. So therefore, the f is the 0 function, which means that this operator lambda minus a is in fact injective, so it has only a trivial kernel, which implies for an endomorphism of the same of a finite dimensional vector space into itself that it is also surjective, or it has full image, which gives the full range condition, which was the condition 2 in our Hille-Yosida theorem. Okay, now I have to still give you this algebra that leads to this particular representation of this second term. Okay, we write out this double sum. And first step is to write out this double sum as 1/2 this sum plus 1/2 the same sum. And then in the second factor, I just swap the row in which, or just multiply inside the fj minus fi term, I just multiply with a -1, which produces a -1 in the front. This is just multiplying inside this bracket for the second 1/2 term with a -1 and pulling the -1/2 out of the front. The next step is to leave the first part unchanged, but the second part now is that I replace, since it's just a summation with respect to I and j, I can just make a relabeling of the index I and j, so I just make an index swap in I and j, which is fine because I'm taking a double sum between I and j anyway. And if I do a relabeling, I'm ending up with this Cij using again the symmetry of the C's. After relabeling, I get the Cij, fj minus fi multiplied with fj. It's just relabeling. And if I then compare, I find the fj minus fi showing up here again. And here I have the fj and the fi, but it comes here with a negative sign, so I can collect the terms as a joint fj minus fi for the second parts, which meet the fj minus fi as a prefactor. So altogether this gives this representation. Okay, that concludes the surprisingly complicated argument, but successful argument, why this operator satisfies the full range condition, which is the condition number 2 to be checked for the Hille-Yosida-Ray theorem. And what remains to be checked is that this operator A satisfies the weak maximum principle, which is condition number 3 in this Hille-Yosida-Ray theorem. For that purpose, let us fix a function f from the domain of the operator, which in this case is the full n-dimensional Euclidean space, and let us pick a coordinate j in which this vector is maximal in absolute value. Then AF, or it's just maximal, then AF applied at that, AF, which means applying A to the vector F and evaluating this at the same spot where the maximal value is attained, is written according to definition like this. It's the sum with respect to all j's of the Cij times fj minus fi. But recall that at position I, which is the one which we single out here, the f vector has a maximal coordinate, so therefore these differences here are all non-negative differences, so they are given non-negative numbers. And as a consequence, since I still multiply here with a positive number or non-negative number, multiplying these negative differences with these non-negative prefactors and summing up altogether gives a non-positive number, which is exactly what I wanted to see for the maximum principle, for the weak maximum principle to be satisfied. So altogether, this operator is a Feller generator on this finite state space, And I leave it as an exercise to show that the corresponding semigroup is in fact exactly this matrix exponential that we had already seen now in the previous exercise. Namely, it's just this exponential series that we can write down for a finite or for a bounded operator. We can just take these sum of powers, this weighted sum of powers of this operator or this matrix A, just in an analogous way as we know it from the exponential definition of the exponential function. So that is the matrix exponential, and I leave it as an exercise to show that this family of matrix valued, or this family of matrices, in fact, which we can understand as a family of operators on continuous functions on this finite state space, that this is in fact the associated semigroup which is induced from this generator A.